Yeah, thank you very much, Robert, for the introduction, and also thank you for the invitation to talk about a really interesting non-destructive testing technique, active thermography. Yeah, my name is Matthias Wolf, and I'm currently working as a research assistant in the research group for thermography and non-destructive testing at the University of Applied Sciences, Upper Austria and Wels. And our main field of research are thermography-based non-destructive testing applications in various industrial fields, but primarily in composite materials. We are also one of several scientific partners in the CAPE project PSSP, where we focus on thermographic investigations on metal parts. That's why we'll talk today about the topic novel thermography solutions for NDT on metal parts. Yeah, I've split my talk into 3 parts because I'm not sure if everyone is familiar with the non-destructive testing technique, active thermography. I will start with a brief introduction in the first couple of minutes, and I will then continue with the main part of this talk and discuss various methods and aspects that have to be considered when utilizing active thermography for the inspection of metallic samples. And finally, at the end, I will show some applications and results. Yeah, as mentioned, first of all, I would like to give you just a really brief introduction into the topic of active thermography, if someone should not be familiar with it. Simply described, active thermography relies on the principle that some sort of thermal excitation will cause a change of the surface temperature of an object that is observed. And by observing the infrared emissions that are related to the surface temperature, this technique can not only non-touching but also imaging-based determine features that are below the surface. And that principle is based that the measured transient temperature characteristics are related to thermophysical material properties, but also to flaws that disturb the heat propagation process. To provide a general example, this animation on this slide shows one of the most typical applications where it is aimed to detect hidden hole, for example, inside the sample. This principle uses an optical-based thermal excitation method, or to be more precise, 2 flash lamps. And by externally increasing the surface temperature of the sample, the temperature gradient inside the material causes a heat diffusion process. And this might be affected by hidden interfaces inside the material, such as defects, and that characteristic can be observed using an infrared camera. The most frequently utilized method of thermal excitation is usually optical excitation technique, for example, by using flash lamps or halogen lamps, or also laser diodes. But of course, there are a wide variety of other methods, just to name a few: ultrasonic excitation or also eddy current excitation. Thanks to a huge development in recent years in high performance equipment for thermal sensing, nowadays, especially scientific grade infrared cameras are available that are able to record in a megapixel resolution, and state-of-the-art quantum detector-based cameras also allow really high-speed frame rates. Yeah, furthermore, utilizing, for example, macro lenses or extension rings allows to observe even very small features. For example, as shown on this slide, on this example, we were able to achieve a spatial resolution up to 17 micrometer on a silicon wafer. Yeah, and especially these recent developments and allowed thermography to be used in a really wide variety of industrial applications. Now I want to move on to a more specific application case, and that's thermography in combination with metal parts, like the main topic of my talk today. And as mentioned before, active thermography is based on two main aspects. One of them is the thermal excitation part, and the other one thermal sensing. And in the case of metallic specimens, there are often additional careful considerations required in both of these aspects. Yeah, it is the same issue in every metrological case that it is required to reach sufficient signal levels of the measured response signal to really reliable determine informations of interest. In case of thermography, that means we need sufficient thermal excitation to reach large enough temperature differences that can be measured. In the case of metallic examples, however, the unique property of metals that they do usually have a higher reflective surface makes especially the absorbance of optically induced energy kind of difficult. Hence, we need like rather long excitation pulses or even additional coatings of the sample to increase the induced energy. On the other hand, the common characteristic of metals is the rather large electrical conductivity, which allows to utilize a powerful excitation method based on eddy currents. This principle is shown in the bottom left part of my slide. Typical eddy current thermography setup, where eddy currents can be directly induced into the sample, and if there should be any material interfaces such as cracks, they do interact with the eddy currents and lead to a change in the current density. And based on this principle, defects can be easily detected, and that is one of the main benefits of metallic specimens. Yeah, as mentioned before, also the thermal sensing part of metals can be challenging in some cases, as shown in this figure, in the middle figure on this slide. Well, in general, we do actually not sense the temperature of an object by using infrared cameras, but we measure the infrared emissions. And of course, the infrared emissions by the object are related to its temperature, but there can also be effects like transmission or reflection that interfere the measured data. Yeah, and usually only the temperature-related infrared emissions are the primary quantity of interest. That's why it's sometimes difficult to get just that part of the measured signal. For example, as shown in on the two pictures on the bottom right side of my slide, there we have a metal specimen with where we applied black coating on one of the sides and reheated the sample using eddy currents. Of course, this design of the inductor does not provide a uniform surface excitation, but nevertheless, it should be expected that the surface temperature is kind of the same on both sides of the specimen. However, as you may notice, the apparent temperature, or to be more precise, the measured infrared radiation is larger at the coated side of the specimen, which of course is just due to the varying surface emissivity of the sample. And this is also an important key aspect that has to be considered. Yeah, in the worst case, if the surface is totally reflective, as shown at the figure on the top right side of my slide, you can even see the infrared camera, and in the middle there's the actively cooled camera sensor. Yeah, these key aspects are already challenging in some cases, even if the object is stationary, but are especially challenging when it comes to measuring moving objects using thermography. There it is necessary to provide additional preparation, for example, to use an inclined camera viewing angle, or to cover surrounding infrared radiation to provide rather uniform reflections in the field of view. Another really important aspect is the rather high thermal diffusivity of most metallic metals. These do cause very short diffusion processes, for example, in comparison to non-metal materials, and hence we require usually rather large, high frame rates to achieve the required number of samples in a certain period of time. However, this parameter, the frame rate as a measure of the temporal resolution, also affects other critical parameters, for example, the spatial resolution, but also the thermal resolution. And especially the high frame rate might require to reduce, for example, the integration width of the camera, which is a parameter that is similar to an exposure time of a conventional camera. And as you might guess, this change affects also the noise level of the acquired data and also the thermal resolution. On the other hand, one benefit of lowering the integration width is the reduction of motion blur, which is shown on this slide, where the same rotating object is recorded at 3 different exposure times. Unfortunately, the frame rate is also related to the spatial resolution due to the limited pixel burst of the camera. The pixel burst is a characteristic that describes the maximum number of samples of all pixels in the field of view per second, and is usually limited by the speed of discretization. And hence, high frame rates might require to reduce the field of view, and to still have the same view on my object, I might have to vary the working distance, which hence affects my spatial resolution. And these effects, key aspects, have to be considered, especially if I have fast conducting materials, especially metals, which might be moving at the same time as shown on this slide. Yeah, now I want to continue with some examples to show the capability of active thermography for the inspection of metal parts. As mentioned before, especially for metals, it's really beneficial to use eddy currents for thermal excitation. And on this slide on the left side, you can see a typical setup where we placed a metallic specimen on the bottom and put a mid-frequency inductor on top of it. And by positioning the inductor in such a way that the direction of the eddy currents which is shown here, are almost approximately perpendicular to the crack direction, we can achieve really large temperatures at the tip of the crack, which I have highlighted here. This crack causes interface in the material. That's why the eddy currents are disturbed, and the current density reached the largest peak at the tip of the crack, which is located approximately here. And hence we can expect also to reach really high temperature peaks in this case, as you can see in that figure that shows the surface temperature of the sample. There's also a wide variety of processing methods to additionally process the recorded data. For example, these processing steps allow to detect and for the segmentation of the total crack, we used, for example, a method called discrete Fourier transform, and based on the generated phase images, we can really good highlight the crack itself. To continue with a more sophisticated evaluation method, we also tried the application of the so-called virtual wave concept, which is a reconstruction method that provides the information about the initial temperature distribution, also inside the sample to some extent. And this method can be used to gain more insight in the actual heat diffusion process, and allows also to implement physics-based segmentation. I generated a small animation here, which should help to highlight the heat diffusion process due to the interfaces in the crack, but also on the edges of the sample. The heat is accumulated and propagates towards the middle to the sound parts of the sample. Yeah, another key benefit is that these result images are almost similar to the B scans of ultrasonic measurements, if you might have noticed, and these results can hence also be used to estimate the thickness of the sample or to determine thermophysical properties. In this case, the crack it's just a normal crack that goes to the bottom of the part, but if the crack would be inclined or has a limited depth, it would be also possible to characterize the depth of the defect to some extent, or also the angle. Yeah, another example is shown on this slide, which should demonstrate the capabilities when applying active thermography on moving metal parts. In this case, we have a saw plate, a rotating saw plate, and it is also a perfect example of the high reflective surface properties of metals, and without additional covers that were used for these measurements to block infrared emissions from surrounding elements, we would have significant non-uniform reflections in that field of view, and it would be hardly possible to remove them during post-processing. Yeah, if you're familiar with eddy current thermography, the eddy currents usually interact at all material interfaces, so also at the normal slots that are visible on that saw plate. But due to the especially sharp interface of the crack, which you can see at the bottom left picture on that slide, I'm not sure if you can see it in UFU as well. we get significantly large temperature peaks at that location. The top figure on the right-hand side is a slow motion animation of the recorded data. Maybe you have spotted the large temperature peak of the crack before. If not, I have slowed down this animation shown at the bottom part and also used just a plain defect contract-based approach to for the segmentation of this crack. Yeah, this works really well in case of metallic specimens. So it's really easy to detect and characterize the defects to some extent for metallic specimen too. The last example, we also inspected a sample out of steel, a steel slab that has a rolling defect in the middle on the front surface. And we used different excitation methods, for example, high frequency eddy currents, an optical method based on a diode laser, but also mid-frequency eddy currents. Yeah, you can see the comparison between a plain visual inspection and the thermography-based inspection on that slide, and especially with especially at that view where the surface corrosion was not removed, you can hardly spot the defect by visible inspection. But if you apply different thermography-based inspection approaches, you can clearly see the hidden defect below the surface. Yeah, and it doesn't really matter which kind of excitation we use in that case due to the corrosion of that surface. Also, optical-based excitation methods work really well. Yeah, this is the last slide of my talk, and there we also tried to utilize the previously mentioned virtual wave concept. The results of two different regions are shown in both figures on the bottom part of my presentation. On the right-hand side, we inspected the sound region, where you just have similar to B scans of ultrasonic inspections of the back wall, but also of the front wall. And these data could be used, for example, to determine the thickness of the material, but also material properties, for example, the thermal diffusivity. We were also able to look at the region where one of the defects occurred, that is shown on the left-hand side of the slide, where you can clearly see also a reconstructed interface where the defect is located. And this information could also be used to estimate the approximate depth of the defect. Yeah, just for comparison, on the top right side of this slide, you can see a cross-section of that defect, and this figure was generated using computed tomography. Yeah, thank you for taking time to listen to my presentations, and if you have any questions, please let me know.
Thank you very much, Matthias.